everybody. Just to let you know, we're going to try to start all the lectures on the dot. So please try to be punctual. Okay? So last time we talked about this idea of geometric complexes in abstract simplicial complex. Right? So in both cases, either a geometric or an abstract simplicial complex is a set K. In geometric land, K is a subset of a large enough Euclidean space, and K is essentially a set of simplices. So it's a set of geometric simplices. So what are those? So those are things that look like sigma equals U0 through UK. This is a K simplex. And this is the collection of all affine combinations of these U's. And here I just want the UJs to be in 0, 1 and to add up to 1. And then the U's are, we ask them to be affinely independent. Which means that if you take U0 minus U1, U0 minus U2, all the way up to U0 minus UK, the K vectors you get are linearly independent in the linear algebra sense. So this is the geometric simplex, and then what we ask is that if you take sigma 1 and sigma 2 in K, then either sigma 1 intersection sigma 2 is empty, or a common phase. Right, so this is sort of the geometric picture of simplicial complexes. Again, we want them to be in some Euclidean space so that we can think about geometric simplices, and then we just need to be careful of what the incidence conditions are between those simplices. Okay? So that's the geometric picture. We also had sort of this abstract picture, which is just a collection of finite sets, and we ask that this is closed under taking phases. Which means that if I give you a sigma in K, and I take a phase of this, meaning a subset, which is not empty, then tau is also in K. This condition we also want it to be true in here. We also want it to be closed under taking phases. Perhaps let me do it like this. We want this condition to be true for the geometric case as well, right? The taking phases stays in the complex. And we know that we can always go from here to here. We can always realize it if the complex is finite. So there is a path from here to here, which is called the realization, which is just the same. And we know that we can do it in R 2 times the dimension of K plus 1. Okay? So that's essentially what sort of the setup of simplicial complexes we started with last time. And we saw sort of two examples of how these appears in the analysis of data, right? So from data, we started with a data set and the distance, and we defined the Briggs complex of x. I'm going to emphasize the distance here to say that these are the sigmas inside of x. This is non-empty infinite, so that the diameter is less than alpha. And this is the Riggs complex. There is another construction we saw, which is called the check complex. So this is the collection of sigmas in x with the same condition, non-empty infinite, so that when you intersect the balls center at points in sigma of radius x, you get something that is non-empty. This is called the check complex. And the last comment I made was that these are sort of two ways of going from data to geometric objects, right? So we have these two abstract simplicial complexes. We know that we can realize them as geometric things if we wanted to. And the comments I made were as follows. We said that these guys are very easy to compute because we're just checking diameters, we're just checking pairwise distances. And then this guy was harder to compute because you have to check this condition of find non-empty intersections. This is harder to do with the computer. However, this grows very, very quickly because we're thinking of sort of all the sets, all the subsets of x, so that grows like to the size, so to the size of x. And these grows a little bit slower, but then you have this problem. So what I want to do today is I want to say a few more things about simplicial complexes, in particular a couple applications. So more on simplicial complexes. And I want to start thinking about at least the idea of homology, which is related to this idea of the Betty numbers that we discussed in the first class. Okay, so that's the plan. Okay, any questions before we begin? Okay, great. Right. What I want to do first is I want to say why we would care about this complex. I want to give you at least a theoretical result that says that this has nice properties. So it turns out that the check complex is a particular case of a construction called the nerve. So nerve of a family of sets. So I'm going to so suppose that you have U, which is just a collection of sets. I'm going to define the nerve of U so now here this is called the nerve of U. It's going to be the collection of subsets of J, where this is finite and non-empty, so that the intersection of J's and sigma of the UJ's is non-empty. So again, you start with any collection of sets, Uj. They are indexed by this indexing set uppercase J, and then we're going to create the following collection. The nerve of U is going to be the collection of finite non-empty subsets of J, so that the intersection of the corresponding UJ's is non-empty. So hopefully it is not that hard to see that this is essentially the check complex for a particular collection of views. Right, so in particular, this is so in particular here, the check complex at alpha rho is the nerve of the collection of open balls. Center at points in X. So I'm going to give you one theorem that is super useful in topological data analysis. By the way, this is a simplicial complex. Okay, an abstract simplicial complex. So the remark. The nerve of U is a simplicial complex. Here's the theorem I want to provide to at least describe one of the properties that makes these complex nice. Yes, go ahead.
Is it an abstract?
Abstract. Yeah. So again, every time I say simplicial complex, I mean abstract simplicial complex. If I mean geometric, I'll say that. Okay. So here's the theorem that I want to give you today. This is sort of, I'm going to call this the baby nerve lemma. It's not the actual name, but hopefully the word baby emphasizes that there's a bigger version of the theorem. So the baby nerve lemma is the following. It says that if I take, so let X be a collection of points in Rn. Okay? I'm going to take the collection of balls of radius alpha X, because before is going to be the points, Y in Rn, such that the distance in Rn is less than alpha. So this is for a little x in X. Then the union of balls center at points in X of radius alpha, and the geometric realization of the corresponding check complex, or the nerve complex, then these and that have the same topology. Let me say a few words about this result. Okay, so we imagine here that sort of our ambient space is Euclidean space. That our data, the data that we collect, is just a bunch of vectors in Euclidean space Rn. If this is the data, then probably one can think of it as being sampled from some continuous ground truth that we don't have access to, but that we would like to find. So let's say that the picture is this: that perhaps you have a continuous object, a torus, and then the data is something that is sampled, maybe with noise around these toys. Okay? So for the physicists in the room, so maybe you have a set of equations that describes the data points that you observe. Then the surface that I'm showing here is the collection of all the points that satisfy those equations, right? Some continuous object. And what would you like to find? You would like to find the underlying truth given the data that you observe. Okay? Or maybe for the machine learning people in the room, you have the classification task, cats versus dogs, images of cats versus images of dogs. So maybe this side of the data is where most of the pictures of cats live, and this part of the data is where most of the pictures of dogs live. And if you were able to parameterize the ground truth, you could say something about the learning task. What does this theorem say? It says that if I now look at every point in my data set and draw a ball of radius alpha around it, and take the union. And so on. So these are the balls of radius alpha. So what the theorem is saying is that the region covered by those balls has the same topology as the thing that we would construct using the nerve complex, the simplicial abstract complex that we can do with some work. What do I mean by the same topology? We haven't defined that yet. But the intuition is that they have the same number of connected components. They have the same poles. They have the same structure that I keep when I deform continuously. Yep.
So maybe I'm missing something currently, but what is the structure of the nerve complex? I know that it has the same topology as this abstract thing we could ship, but what is it actually, if we were to look at this diagram, what is actually the nerve complex that we're looking at?
Okay, yeah, let me explain that. So the nerve complex, maybe I should draw a picture. So it'll have, right, so it's all the subsets of J, right? All the subsets of J, finite and non-empty, so that this is true. I'm going to do it for this guy here. So let's think about the nerve of... Yeah, go ahead.
Can you even draw it?
I'm going to try. I'm going to try. And hopefully not fail.
Probably just name the points A, B, C or something.
Yeah, that's what I'm trying to do. So say that the data is these points here. Okay, that's the data. The nerve complex is going to have one vertex per point in X. Okay, so that's the first step. Use all the points in X as a vertex. Now the thing you're going to do is you're going to draw balls of radius alpha around the points. And perhaps like that. Okay? The next thing to do is to ask, what are the edges of this complex? You're going to have an edge every time two balls intersect. Right? Because he's saying, let's look at it here. Right? So say the set with two edges, maybe A and B, is going to be in here if the balls center at A and center at B have non-empty intersection. Okay? And we have this guy here because this ball also has intersection. There are no more edges because there is no more empty intersections, non-empty intersections. Now, if you have three balls and they all intersect in a non-empty way in here, then you add the two simplets. And that's all I can do because there are no other triple intersections going on. And in fact, this is the complex for this data set in that radius. Okay? So geometrically, the way to think about it is that every element of the indexing set is going to give you a vertex. You're going to get edges if two of the corresponding sets intersect. You're going to get two simplices if two of the sets intersect in the same entire dimensions. Yes?
Could it be said that rather than the check complex being a subset of the nerve, could it be a geometric realization of the nerve complex?
No. So I guess what I'm saying here is that the check complex is a particular case of the nerve. So what I'm saying is that there's a particular choice of use In fact, if you let the U's be these balls, then you recover the check complex. That's all I said. Like here I'm giving you freedom as to what the U's are, and in here I'm telling you that the U's have to be balls of the same radius. Okay, that's one thing. And the thing to notice is that both of these things are abstract, right? Like I haven't given coordinates to the vertices in here. There's no Euclidean space involved. But the theorem, the baby nerve lemma, says that when your data is in fact in Euclidean space and your balls are in fact Euclidean balls, then the geometric realization of this abstract thing recovers the topology of the region that it covers. Okay.
Okay. Is that true for other norms there?
It is true for other more general settings, but we'll get to that when we have enough material. Okay. I want to stop here, and I want to give you a few applications of these ideas of complexes and so on. Is there a question? Yeah, go ahead.
What topology do we use in the union of balls? Do we use
The Euclidean topology.
Okay.
Right, so this is a subset of Euclidean space, and you just take the subspace topology. Yep.
Does this work in non-Euclidean space?
Yep. But you have to put some conditions for this to be true. We'll see that hopefully soon. Okay. So let's try to get these. Okay. It should just use one. Okay. So I want to give you a few applications of how these ideas of the nerve complex can be used in data science. Let me turn the lights off. Okay. Okay, so learning with nerve complexes. So usually, this is the picture of data we have. It's just a collection of data points in some ambient space. So again, the ambient space maybe is Euclidean space or something more complicated. If the data is very large, usually what we do is we select a subset of the data that perhaps represents the distribution that we have. And at least in topological data analysis, we're going to usually put open balls around the points we choose. Okay? And those are the U's, or at least an example of the types of U's that we can take in the nerve construction. So once we have these sets U, I'm going to call the region covered by the balls, I'm going to call it V. Okay? And I'm going to request that we have a partition of unity associated to this collection of sets. Let me explain what that is. A partition of unity associated to that collection of to this collection U is a collection of functions phi j. You get one per ball, and the functions go from the entire region to 0, 1. And what we're going to ask is that they add up to 1 everywhere, and we're going to also ask that their support is contained in the closure of the sets. What does that mean? It means that if you look at where phi j is not 0, that only happens in uj. In other words, phi j is 0 outside of uj. Okay, so that's called a partition of unity. Here's an example of a partition of unity that one can put just in a data set in general. So imagine that your U's are open balls, like in this case, balls of radius alpha. Okay? Then what I'm going to do is I'm going to take the following collection of functions. And let's just stare at that for a minute. It looks complicated, but it isn't. So let's go in steps. What is this plus? It's just the positive part of a real number. Okay? So it's 0 if lambda is negative, and it's lambda if lambda is positive. So what is this expression doing? It's saying if my point B is very close to xj, right, then say that this is 0. Okay? So if this is 0, then this is essentially lambda. Sorry, alpha. Okay? Now, if this is very large, say that is, like alpha plus something else, then this becomes negative, and the positive part kills it. So the way to think about this, or at least one way to think about this, is a cone that is drawn to be supported on the ball. So if this is uj, then this expression is essentially this: a cone that goes to 0 outside of the open set. And here I'm just adding up all those cones so that this is in fact a partition of unity, so that it adds up to 1 everywhere. Okay? So that's just one example of a partition of unity that one can create explicitly. Okay? Yep.
So I'm not a mathematician, but
Yep.
that looks like a distribution.
It looks essentially like a distribution. That's a very good. This thing in the denominator looks like a density estimator, right? Like if you were fitting a distribution. That's a very good comment. So you're like splitting the distribution between the balls. That's very good. Okay,
So what's uppercase J in there, K and J?
it's just so uppercase J is the collection, is the index in set,
Okay.
right? So if you have n balls, then J is the set 1 through n.
Okay.
Okay, great. So that's a partition of unity. So what do we have? We have the data set, which is the black dots. We've chosen some special data points, which are the red guys. We've put balls on the red guys, and we've created a partition of unity. Maybe through some statistical methods, or if you're more naive, through the cones that I just described. Once I have the open balls, I can also construct the nerve of those sets. So remember that you're going to have one vertex per open set. You're going to have an edge every time 2 sets intersect. You're going to have a 2 simplex every time 3 of these guys intersect, and the same in higher dimensions. Now, yes, go ahead.
What happens when 4 intersect?
Then you get a 3 simplex, and we cannot visualize it in the plane,
Okay.
but we can certainly do it in R7
Okay.
in general. Okay. So I'm going to create a function from B to the geometric realization of the nerve. And I'm going to do the following. I'm going to take a little b in B, right? And I'm going to evaluate it on the partition of unity. And now this seems hairy, but it isn't. Let me say what I mean there. Okay, so I want to erase this yet. So remember what happened when we had a geometric simplicial complex. So hopefully what we remember is there's a connection K of Rn, and this is made up of a bunch of geometric simplices. Okay? So if I give you a point x in K, okay, then it will be, so there exists, so maybe, there exists a simplex, let's say, sigma in K, such that x is in simplex. Okay. Now, let me write this guy in terms of the vertices that compose it. So let's say there is a K simplex. And let's remember that this is the collection of convex combinations. So if x is of this, so if x is in here, right, then you have to be able to write it as this sum for some choice of lambdas. So there exists lambda 0x to lambda kx such that x is equal to j from 0 to k lambda lambda j x. So what we've done is show that every point in K can be written as this convex combination for some choice of lambdas. One can also show that this choice is unique. So lambda 0x, lambda kx, and sigma maximum dimension are unique. I can say more about this uniqueness result, but for now the only point I want to make is that every point in the complex can be seen as a convex combination for some collection of the vertices. And the coefficients that you're using and the actual vectors that appear are that choice is unique. That's the message. Okay. So what am I doing here? I'm saying take a point B in B, and we're going to evaluate it in the partition of unity. Right? We're going to evaluate it on these guys. We know that all of these guys add up to 1. So in particular, they're going to give us lambdas, correct lambdas, to place our point in the complex. So what I've done is provide a way of mapping the data onto, oops, this is that bad, of mapping the data onto the complex. Right? Yep.
So this isn't, why are you calling it a nerve complex? Why are you not calling it a check complex? On the,
because every check complex is a nerve complex for some particular choice in use. So I'm not trying to play semantics. It's just something. But you're right. Since I'm making if we make the choice that the views have to be balls, then this will be a check complex. But I'm doing it here in general, saying that whatever you choose in here, you get a nerve complex. Whatever you did, you can choose partitions of unity, and in that situation, you get a map into the geometric realization. Yep.
So visually, is this geometric complex? So it's taking so anything that's only, so for example, we take that one ball, yeah, right there. Any of those points that are only in that ball are plotted onto that point.
Onto that vertex, correct.
Yeah,
Correct.
Exactly.
Correct.
And then on the line, it's anything that's in the intersection, and
it's distributed. It's distributed according to the partition of unity.
And then the middle, it's the ones that are in the intersection of all three.
Exactly right.
Okay.
Exactly right.
So that's what's actually.
That's what's happening. That's what's happening. And the partition of unity controls where you land.
Yes.
Correct.
Okay. Yeah, it's like it's like some sort of metric for how far you are away from
the vertices.
Yeah, for the vertices.
That's
Okay.
exactly right. Yep.
So do I lost some information in this process?
A little bit. So from the baby nerve lemma, we know that these two guys have the same topology, for example. If we created the partition of unity using the distance function, right? Then the position of the points also retains some metric information from the original data set. But as Joe mentioned, notice that all these points that are only in this ball, all of them get mapped to the same point. So in particular, this map is not necessarily injective. So things may get collapsed. That's what we lose. Okay? Very good question.
Yeah, so like, okay, so there really aren't like, it seems like you drew multiple points there. That's just to show there's multiple points.
Exactly, that several points in here mapped to the same point.
Yeah, but when they're in there, they're
It's
really
just one
the
point.
same
It's
thing.
just one point. Correct. Yep.
So this could be seen as a way to simplify the data set in a way that preserves its topology.
Exactly right. That's exactly right. One thing to notice is now that this guy over here looks like a space that is locally linear, a locally linear space. Does that make sense? Where you have straight lines. This data set didn't have to come from some linear space. So this is one way of locally linearizing your data. Let me show you something else. Okay, so once we have that, we can do one more thing. So let me explain what I have in here. So now these are in A, I'm showing the data and a collection of open sets covering the data. So again, they don't have to be round balls, they can be other sets. Okay? In here, I'm showing you the partition of unity, right? So it's saying that, for example, this guy in here, the partition of unity is very high and then drops down and is 0 outside this set. And I'm doing that for each set. Okay, so this is a pictorial way of doing the partition of unity. Here, I'm showing you both the nerve complex and the result of mapping the data onto the nerve complex using this partition of unity. Okay? I haven't explained what D and E are. I'll do that now. How many of you have heard of the graph Laplacian? Okay, a few people. A few people have heard of the graph Laplacian. Let's say what it is right now. Okay. This is a super useful concept, and you should Google it later after class if you want to know more. Not graph, but graph Laplacian. Okay, so what we're going to imagine is that we have a graph. And the vertices are, let's say, J and K. Now, for every edge in my graph, I'm going to have a weight. So this is the weight of the edge, J and K. We're going to require, I'm going to do it for graphs that are that do not have orientations. So in particular, I'm going to require that WK is the same as KJ. And I'm just going to ask that these be non-negative. So in particular, I can think of this collection of weights as a matrix. Right, so this is the weight matrix. Where the position JK has the weight of the edge JK. And the matrix is symmetric, right? I'm asking that JK be equal to KJ because we don't have directions. So that's the distance that's the weight matrix. Okay? I'm going to define the degree matrix. And the degree matrix is going to be a diagonal matrix in the jth And the jth component, so this is called the degree matrix. And then the jth component is going to be the sum over k. In other words, you take the vertex j, you want to know the degree there, and what you do is you add up the weights of all the edges that are incident to j. Now, the Laplacian matrix is the degree matrix minus the weight matrix. At least one version of it. The graph Laplacian. This seems weird, and there's a lot of research in understanding the properties of matrices like this. What people are often interested in are the eigenvectors of these matrices, the eigenvalues and the eigenvectors. So we're interested in vectors u that satisfy the eigenvector equation. Right? So here lambda is just yep.
What about the diagonal elements of W? Do we?
They can be 0. I mean, the sort of JJ
Yeah.
can be thought of as the weight of the vertex,
Okay.
right? So you can assign weights to the vertices as well. Yep.
Is there, so the two halves of the matrix are redundant, so is there a way, what, the top half is equal to the bottom half?
Yeah.
So is there a way to like formulate this that, I don't know, never mind, forget
It's
it.
easier to do it this way, but I get what you're saying. Okay, so we're interested in the eigenvector problem, and what is the reason? So what is the first question is, what is the size of this matrix L? Right, it's going to be a square matrix of size, the number of vertices by the number of vertices in the graph, right? So in particular, U is a vector whose length is of the number of vertices in the graph, correct? Now, the vector U is essentially telling you a real number per vertex on the graph, okay? And here is something we can do. Now we're going back to nerves. Here's the nerve complex, right? If you forget about the higher simplices, higher dimensional simplices, you can just look at the underlying graph, right? So that gives you a graph. There are, of course, ways to weight the edges. For example, you can count the number of points that you have in here. You can measure the distance between the vertices, between the centers of these sets, right? So there are ways of saying how important each edge is. It is not super important how we do that, but there are ways of doing it. Okay? So there's ways of putting weights. If we have weights, then we have graph Laplacians. Okay? And if you have graph Laplacians, we have ways of finding interesting functions, those eigenvectors, interesting functions on the vertices of the graph. What we can do next is interpolate those values. Right? So what we're doing here is we're taking eigenvectors of the Laplacian and we're turning them into functions on the nerve complex. Right? This is actually one of the eigenvectors of the Laplacian for this graph. This is a real eigenvector. Why do people care about these eigenvectors? Because they encode the underlying topology. For example, they encode things like disconnected pieces. They encode things like loops in the complex, right? So these are very geometric and topologically meaningful vectors, yes?
So going back to that example with the torus and how you were saying that if a physicist were to understand it, this is a set of all points, it's the surface of all
Functions.
points that satisfy these functions.
Yeah, yeah.
These eigenfunctions would reflect those
That's exactly right.
physical functions.
Yeah. So for example, to give you a simpler example, if your data was just a circle, right? The eigenvectors of the Laplacian look like sines and cosines of different frequencies, right? Which the physicists know those are the eigenfunctions of the actual Laplacian. Okay. now the last step here, so hopefully I've explained D. So D is essentially computing the eigenvectors of the graph Laplacian and then interpolating linearly on each one of the simplices. Right, so now we get these colors in here. By precomposing with these, with the map given by the partition of unity, we can move this function to a function of the original data set. Okay, so that's where we're at. Okay, how are we going to use this? Imagine that your data, which we've mapped to the geometric realization of the nerve complex, comes with labels. Right? Maybe not all the data, but some of the data has labels. I've indicated the labels as colors in here. Right? So for example, again, some of these are dogs, some of these are cats. And the rest, you just do not know what the label is. Right, so data, label, and unlabeled. So I'm going to do something that is called semi-supervised learning. In that I'm going to try to learn with all the data, even though only a portion of it is being labeled. Okay, so here is a toy example. So here are two data sets. The spiral data set, and these are concentric circles. The colors mean the two classes on each data set that we're going to try to learn. We're going to try to train a classifier to tell the red points from the blue points and the red points from the blue points. There's a bunch of blue points in here. It just looks very concentrated. So I'm going to do what I did before. I'm going to construct from the data, I'm going to construct the nerve complex. I'm going to construct the graph Laplacian on that, and I'm going to use the eigenvectors of the Laplacian as functions of the data. That's a mouthful, but this is what comes out. So the colors are supposed to tell you the functions on the data that came out of these Laplacian eigenfunctions. So hopefully you can see that this eigenfunction already separates the two classes. And similarly, this eigenfunction already separates these two classes. And these are all their eigenfunctions, right? So this looks like maybe like a sine or cosines or combinations thereof, right, like here. These are very, exactly, I'm showing you 9 eigenfunctions on the data. And just one of them, just using one of them, we were able to separate them. But we can also just train, like a linear model using these features. And we would see that this is the most important feature for the classifier. Okay? So here's the accuracy of classification. Depending on how noisy the original data set is, then you get sort of near perfect classification accuracy, as we should. I should point out that the spiral data set is particularly challenging for just feed-forward neural networks. There's a very cool app so there's a web-based version of TensorFlow. If you Google TensorFlow Playground, you'll find it. And this is one of the examples. So they let you train a feed-forward neural network to classify these data sets. And what you see is that it's actually difficult to tune it to do it.
Is that why people have difficulty sometimes too with distinguishing?
People have many difficulties. But nonlinear data is difficult. That's just what it is. Yeah.
So maybe one more question. What associated with these other eigenfunctions? How did you get all these eigenfunctions?
I just got it, yeah. I just solved the eigenvector problem and just plotted whatever I got.
Gotcha. So you actually had to try this multiple times and then one of them just happened to be the one you wanted?
No. I didn't do it multiple times. I did it once. Like I created the nerve complex, found the eigenfunctions, plotted them. This is what I got. I used, without looking at this graph, I looked at the linear model using those features as a classifier, and the results inaccuracies what I showed you before. There wasn't a bunch of times.
Is this done in Python by any chance? Or
Yeah, I think so.
Alright, great. That's good. Okay. I can do this with anything else.
Okay. And then the classification accuracy for the circle and the dot in the middle examples of different distributions. Here's a more realistic example. So we are trying to predict the boiling point from the geometry of a molecule, right? So I'm giving you the atoms, I'm giving you their positions in Euclidean space, and then for each molecule, we're going to try to predict the boiling point, just one number. So this is the data set. The data set is just all the molecules, okay? So originally, we got a fairly small data set, right? So small data set with these numbers, and their boiling point as training data. So what we did is we released a spider on the web to just crawl it and get us a bunch of molecules, right? We didn't know the labels for them, but what that allows you to do is to get a very large data set from which to recover the right nerve complex. Okay, so just get a lot of data, even if you don't know the labels. We use that to construct the nerve complex and to find the Laplacian eigenfunctions. And then we used the actual labeled examples from the original data set to train the classifier, or to train the predictor for boiling point. And these are the results. Let's see if I can view this right. Yeah. So you start with 120 unlabeled data points, 15 labeled data points from which to train your model, and 15 to report on the data. So it's a very small data set. The state of the art on sort of the error, let's say that is 1.92. Let's just have that number as reference. So this is what happens when you use nerve learning plus SVM. This is one thing that we use to train the model. So the error, if you use the original data set, is 3.4. As you get more unlabeled data, you get a better nerve and better Laplacian eigenfunctions, and you start to decrease the error beyond the state of the art without getting more labeled data. Okay? And I think I've gone over my time. Oh, no.
No, you're going to.
Good. I'm good.
You've got a
30
good
minutes.
30 minutes.
30 minutes, yes. I forgot. 30 minutes. Okay, so if you want to know more, this is part of a couple of papers that we started working on last year. The first paper, this geometric data analysis across scales via Laplacian eigenvectors, was sort of developing this idea of looking at the Laplacian eigenfunctions on these nerve complexes and doing it for several scales. That was the first thing. The second paper is these nerve learning using semi-supervised methods, which was, maybe you have a few points that are labeled, but you can still use those to train predictors if you have enough unlabeled data to find the nerve complex. Okay? So those are the references if you want to know more. Yeah?
How many dimensions were there to your data?
I don't remember. This was too long ago. It was last year. I don't remember. Yeah, but I can say more offline. So let me now turn this off. And the moral of the story is that these types of constructions gives you ways of understanding the space in which the data lives. That's the moral of the story. Okay. Let me continue now. Let me start here. Okay, so I was hoping to get a question when I was presenting the whole business of nerve learning. And the question I was hoping to get is how do you choose alpha? how do you choose the scale for your poles? Right? That was the question, but I didn't get it, so we're good. So what I'll do now is try to tell you at least one technique to relate complexes seen at different scales. The concept is that of a simplicial map. Okay, so the definition goes as follows. So we're going to let K and L be abstract simplicial complexes. Okay. Then a function f from K to L is said to be simplicial if every time I want to evaluate f in a particular K simplex, that is exactly the same thing as first evaluating f on the vertices and just looking at the set again. It's a very simplex. One thing to notice is that f does not need to be injective on the simplices. In other words, f0 and f1, for example, may map to the same vertex, in which case these may be a K simplex in here, and this here may be a simplex of smaller dimension. Okay, that's possible.
Wouldn't you want that anyway?
What do you mean, what?
Wouldn't you usually want that so that it reduces the noise in the data?
It depends on the situation you are. It depends on what these complexes mean. Because that could also be seen as loss of information. And maybe you don't want that. So let me give you an example. Actually, before I give you the example, let me give you a remark. Notice that f, if it is a simplicial map, is completely determined for what it does to the vertices. There's a simplicial map is completely determined. Its values on vertices. Because once you know these values, you will know what to do with any other simplex. So here's an example. I'm going to take K to be, x0, x1, and x2. These are the vertices. If I were to be completely, I say explicit, I would put curly braces around x0 and x1 because these are supposed to be sets. But I'm going to dispense with that. We'll understand that these are just vertices. K0, K1, K1 and K2, K0 and K2. So that's K. And then L is going to be K union x0, x1, x2. And I'm gonna let f from k to L be just f of xj equal to xj. So let's see what this looks like. So K has three vertices, 0, 1, and 2. And it's got three edges, 0, 1, 1, 2, and 0, 2. That's K. L has the same three vertices, so it's essentially K union 0, 1, 2. So it's the full two simples. So this is x0, x1, and x2. Then what f is doing is it's sending, x0 to x0, x2 to x2, and x1 to x1. It's just like inclusion of this simplicial complex into this simplicial complex. Okay. So that's a simplicial complex. It's a function between two simplicial complexes, which is completely determined for what it does in the vertices. I want to give you an example from data, how these guys can arise. Yes, go ahead.
Can you take that, like f of 0, 1, so f of an edge?
Will be this edge.
Okay.
Yep.
What's the significance of leaving out x0, 1, 2 in K?
In K is that I'm not including the two simplex.
Why is that
Important? Let's see it the other way around. Okay? I'm going to take the map. I'm going to take the same complexes, but now I'm going to look at J, the function G from L to K. Okay? And it's going to send, it's going to do the same, let's say. So it's going to send xj to xj. And let's look at a couple of examples, right? So you have x0, x1, x2, 0, x1, x2. Now, what is G of x0? Yeah, it's just x0. That's how it is defined. Similarly, what is G of the edge? x0, x1. Well, if it's going to be a simplicial map, it better respect what it does to the vertices. So it should be G of x0, G of x1, which is x0, x1. So it's sending this edge to this edge. What would happen to the face? We're in trouble.
Yeah.
It should be x0, x1, and x2,
Error flow
but this is
for-
not in L.
In K?
In K,
K, right? I mean,
L to K.
Yeah, we're going
Yeah, it's not in K. Great. Thank you. Right, so we failed, or I failed you. Right? This is not. There is no way to get a simplicial map that does this. Right? So, in other words, the actual topology of the spaces constrains the types of simplicial maps I can get. Right? So, for example, something covered cannot go to something with a whole image.
So the abstract version of K would be, the abstract version of L, if we were to represent it as sets, would be K plus x0, x1, and x2.
Union.
Yeah.
Good. So that's the significance. I wanna now say how these types of simplicial maps arise in data. Let me not do it here. F from K to L. I'm gonna do it there. So I'm gonna do it with an example. So suppose that you have two data sets, X, row X, and Y, row Y. So X and Y are the data points, and row X and row Y are the different distances we use for each data set. And we're going to let F from X to Y be a function which is distance non-increasing. Distance non-increasing. What it means is that when I measure the distance in Y between 2 points from X, that is less than the distance in X between the points. For every pair of points X0 and X1. Is that okay? Now, once I have a function like that, I can fix some alpha greater than 0, and I can build the Ribbs complex for X and the Ribbs complex for Y. And again, remember that this is a collection of all the finite non-empty subsets of X that have diameter less than alpha, where you're measuring diameter with this row X. So we're going to define a new function, big F, from here to here, and it's going to send a collection of points x0, xk, right, so something that has diameter less than alpha, and we're going to send it to the collection of points f of x0, f of x. And the remark is that this makes sense because what do we have to check to see that this function actually makes sense? In other words, you want to check that this guy is in here, in this complex. Right? So that amounts to showing that the diameter of this set is less than alpha. Okay? So let's see that. The maximum between all the points, ij, so 0 and k, row y of f xi, f xj. Right? So I'm checking all the distances between these points. So this is, since f is distance non-increasing, then this is less than or equal to max jk of f xi, xj, right? And since these points we said were in the Ribbs complex, in X, oops, not F but row. There we go. And then the distance between any two is less than alpha. Check. Right, so I've shown that the diameter of this guy is certainly less than alpha. So what I've shown is that every time you have two data sets and you have a distance non-increasing function from one to the other, then that function can be extended to a function between Ribbs complexes for any scale alpha. Okay. So this is a simplicial map. note is that F is a simplicial. Okay. We have 10 minutes. Okay, 10 minutes. So what did we do today? So we dove a little bit deeper into this idea of simplicial complexes, in particular the nerve of a collection of sets. There was sort of the baby nerve lemma that says that at least in Euclidean space, the region covered by the sets, by the open balls, has the same topology as that of the nerve. That's a big result. And hopefully I was able to convince you with the slides that one can use these constructions to actually do data science, right? In particular semi-supervised learning problems with very few labeled data. So what we'll do next time is connect this idea of simplicial maps between abstract simplicial complexes. We're going to connect that to continuous functions between geometric complexes. Okay, and see how the two relate. And we'll move